This is Lab 4 bar magnets for Physics 2212. Introduction. So the main purpose was to find the distance dependence of a bar magnet and compare that to the measured result to the equation for our on-axis and off-axis magnetic field of dipoles. So the general magnetic dipole formula is this, and then this is the on-axis and perpendicular. The second two are just simplified representations of the first one. The main result of this lab was finding distance dependence to be n equals negative 3.33, and dipole moment was 1.57 am squared. The general magnetic dipole field formula, this equation is magnetic field of dipole at any observation location, and this formula is used in the coding section of the lab, mainly because it's much more general and can be used for any observation location. The on-axis field formula is a simplification of the general formula that only works for on-axis, and this is just easier for calculations. Same with the perpendicular magnetic field formula. It's the same idea as the on-axis one. It's just a lot easier for calculations, and it's just a simplified version of the overall one. Assumptions. So our main assumption is that the bar magnet we're working with is ideal and produces a perfect dipolar field, and then also that its axis is aligned to the physical axis of the magnet because it's a cylinder. We're also assuming that there's no other magnetic fields that are acting on our phone besides the Earth, and these assumptions just make our calculations easier and we don't have to worry about as much things. Experimental diagram. So the system is the magnet and the surroundings are the phone, the Earth, and everything else. And our initial conditions for the experiment were that we have an unknown dipole moment bar magnet, and then also we have Earth's magnetic field and just standard conditions, U0 over 4 pi, everything on that side is standard. Experimental details. So first we have to locate the magnetometer that's in our phone. So we move the phone near the magnet until the magnetic reading in one axis is maximized, and then we just repeat it for the other axis. And then that tells us where our magnetometer is in the phone, and we mark it with tape. And then we measure it for on-axis for several field strengths, and then we measure the off-axis field by placing the magnet at a 45-degree angle from the magnetometer, as shown here in the picture at the top right. So calculations. So here's all of our data, and then this is the plot that's generated from it. And from the lab instructions, we know that the y-intercept of this line is ln of k, where k is the constants in the magnetic field equation for on-axis. So then we can just substitute everything in, and we get 1.57 am squared. And then computational model, so initial conditions, U0 over 4 pi is the standard, 1e negative 7, mu mag, that's what we calculated from 41.57. Distance, this is from our data, it's the second one here. And then dperp, which is the average from our data here. And then, so the model represents bar magnet as a magnetic dipole, and then finds the field on the on-axis perpendicular and at 45 degrees off-axis. So this is just like the setup and the function for finding magnetic field. This is the on-axis, this is the perpendicular, and then the off-axis here, this is the output. It creates a three-dimensional visualization, and it just calculates everything and then gives us a visualization with the arrows as vectors. So then the similarities between the data and our model that we calculated is that the calculated data from the model is on the same order of magnitude and the directions are roughly the same. The difference is that our magnitudes are quite a bit different. We're off by like about a factor of 2, which is kind of a lot. It's most likely just due to measurement error, because like we found the distance dependence was negative 3.33, but it should be negative 3, so that's probably that's indicative that there's some measurement error running around in the background. So error sources: incorrect calibration of the magnetometer, imprecise measurement, conditions may have changed, we didn't recalibrate, or our assumptions could just fail. Discussion. So if we had not oriented the magnetometer to compensate for magnetic north, then Earth's magnetic field would be like incorporated into our data, and we'd need some way to differentiate from in our results, like what percentage of it is Earth's magnetic field and what percentage of it is actually from the magnet. And then if we stuck to identical magnets end to end, then the experiment should act mostly the same, but the dipole moment would just be doubled because you're stacking the magnets. It just makes a stronger magnetic field based on the superposition principle, so it'll just look, from far away, it'll just look like one super strong magnet. Close by, it'll be slightly different, but from far away, it'll just be like one strong magnet. So finally, we found the magnetic dipole moment for this magnet was 1.5 am squared, and the distance dependence was negative 3.33, and the measured data was on the same order of magnitude as the calculated data, but it was a bit off. This is likely just due to calibration errors or measurement errors.